Alright, so this is our first introduction to waves. This video serves as a way to get some of your basic ideas down, and I will also clear up some common misconceptions that students go into level 3 with from previous years. So this video just ensures that you have all the basic understanding that is needed to tackle whatever comes up in level 3 waves. So firstly, when we talk about a wave, we are talking about a transfer in energy without a net transfer in matter, okay? So in energy without net transfer of matter. There we go. So that's the basic understanding of a wave. The first type of wave that we can have is a transverse wave. Okay, so this is a wave that kind of looks like this. Okay, in this type of wave, the oscillation is up and down. Okay, right, the oscillation is up and down, but the wave travels from left to right in this scenario, but it can also travel in all directions, right? It doesn't really matter. But for this depiction, it's traveling from left to right, okay? Right, we can also have a longitudinal wave. This is where the oscillation and travel are in the same direction. So this is oscillation and the travel are also in the exact same direction. The way this is usually depicted is places of compression and places of rarefaction, okay? Like so, right? So this is our place of compression and these are our sections of rarefaction. And just to clear this up, this oscillation arrow should have both arrow tips, all right? Because the oscillation is going like this. And that again is due to the fact that waves transfer energy and not matter. So if the oscillation didn't go back to where it started, it would transfer matter, right? Alright, so now when talking about some of the basic properties of a wave, there are a few things that we need to note down, okay? So let's draw out a wave like so. Alright, so that is one complete cycle that we have drawn out right there. So you can imagine that if a particle is on here, it will make its way up, right? And then it will come down, and then it will come back to the starting position, right? The mean, okay? Right, and at that point, once it reaches the mean again, the particle would have completed one oscillation. And so therefore, the y-axis will be displacement of that particle, right? So that would be in meters. And then the x-axis would be distance, also in meters, okay? Right, so a few things to remember from our junior years. If we go from one spot to the exact same spot on a wave, we know that that is one wavelength, right? And a wavelength has a symbol we call lambda. And we also know that lambda is measured in terms of meters. Right, we also know that this distance here is the amplitude, and the amplitude is simply a measure of distance from its max peak to the mean position, right? So this is the mean position. This line right here is the mean, okay? So that's the amplitude, right? We should also remember that our max peak is also known as a crest, and our minimum is also known as a trough, right? So our amplitude is also this distance right here, okay? Same value as this. So that is also the amplitude. Now, one thing to be aware of, I have labeled this distance right here from here to here as one wavelength. However, if I were to draw this graph out again, as so, and again we have displacement here in meters, but this time on the x-axis we have time, right? And obviously time is measured in seconds. Now this time the distance between over here and over here is not the wavelength, okay? It's not the wavelength. This time it's the period, okay? So this is one period, which we can symbolize as t, and that is again measured in seconds, okay? Now, I hope that's obvious why this is a period and not wavelength, because along the x-axis, we are measuring in terms of time. However, in this scenario, we are measuring in terms of distance, and therefore it is a wavelength. So although the graphs look the same, what they are measuring is different. And just a way to link these two graphs, there are two different ways that we can get frequency. So just a reminder, frequency is a property of a wave, and it's measured in hertz. Alright, so like I said, there's two ways of getting to it. The first way is through this first picture, and that's by using our wave equation, and we should remember our wave equation is v equals f lambda, where v is the speed of the wave. Lambda, like I said before, is our wavelength. So we have wavelength, right? And therefore f is our frequency. And so we can simply rearrange for our frequency to find our frequency, right? And so in terms of the second graph, we can get to the frequency as we know frequency is 1 over the period. So the reciprocal of the period, okay? And so, like I said, this is frequency, and this is our period, as stated up here, all right? Now, why is frequency important, all right? So why is these values important? Frequency is related to sound, right? Obviously, sound waves. And in terms of sound, it's related to pitch, right? So that is how loud something is, right? The max frequency that humans can hear is 20,000 hertz, sorry, I think. You can search it up to confirm if I'm correct. I'm pretty sure it's roughly that value. Usually when we listen to music, the notes that you hear are anywhere from 100 to 700 hertz, roughly, all right? So that just gives you some scale as to how high the max hearing is for humans, right? In terms of light, we are talking about the color of the wave, right? So violet has the highest frequency and red has the lowest frequency. And we should know from our modern physics, if you took modern physics, we should know that the energy is directly proportional to the frequency, all right? When we talk about light, that is. The wave equation that I stated before, this equation right here, is an equation that you'll be seeing a lot in level 3. As for the speed of the wave, you might be wondering, well, what is the speed of the wave? Remember, the speed of a wave depends on the type of wave, right? So sound waves usually have a speed anywhere in the realm of 340 meters per second. That can change. I've often seen 343, 340, 341, right? These values change in exams. They will be given to you, so don't worry about that. But it's usually in this realm. Light is usually 3 times 10 to the 8 meters per second, so it has 300 million meters per second. It's not exactly that value. If you search it up, it's probably something like 299 something, but close enough for NCEA. On occasion, they give some other mediums other than sound or light. They give sometimes string. Sometimes they give string or a bridge of some sort, right? And obviously, I can't tell you what the usual speed of that is. Again, it will be given to you in the exam, so don't worry about that. But just know the speed of the wave depends on the type of wave and the medium it's going through, okay? And that will be it for this video. See you.